talking about endothermic and exothermic reactions. So let's look at some examples. And you're going to be looking at those examples. You're going to be seeing those examples as well on your exam, on your third exam, of course. So chapter 6 is for exam number 3. Okay. All right. Oops. Exam number 3. All right. So guys, let's take some examples again for endothermic and exothermic. Okay. So for instance, guys, if we start talking about solid, liquids, and gas. So let's say you have a solid that you're trying to change into a liquid, and then a liquid you're trying to change it into a gas. So let's say you have water, solid water, which is ice. You're trying to change it into liquid, and then you have liquid water. You're trying to change it into water vapor, so gaseous water or steam. So if we take our solid water, which is basically ice, then what do we do with the ice to change it into a liquid water? We basically supply heat. So we put in heat to go from solid to a liquid. And the process to go from solid to the liquid, what is that called? So that is called melting. Okay. And what is the process called when you go from liquid to a gas? So when you have liquid water and you try and change it into a steam? So if this is called melting, this is called boiling. Boiling, okay? And then what is the reverse for them called? Like what is it called when you go from a gas back to the liquid? So gas to the liquid, that is called condensation. So that's the opposite of boiling. Now, when you go from liquid to the solid, so what's the opposite of melting called? It's called freezing. Okay. Now, there's one more thing that we need to learn here, is that when you go from solid to gas, that's also a possibility. That's not very common. Usually, when you have to go from solid to a gas, you must go through a liquid. Like you take ice, you change it into liquid water then changes into steam. But actually, for some cases, like in the case of dry ice, you take solid carbon dioxide, which is frozen, just as like as ice. It looks like ice. It's called dry ice. So you take that, and if you actually put it to if you want to try to change it into a gas, it actually directly goes from solid to the gas. It does not go into a liquid. So a solid dry ice never changes into a liquid. That's why it's called dry ice, because it never melts. It directly goes from solid to the gaseous form, and that is called so this process of you changing solid to the gas directly in one step is called sublimation. Okay. Now, when you take a gas, that can also directly go back to a solid with skipping this liquid step. So this, the opposite of sublimation, is called deposition. Now, what was the whole point of this learning this in endothermic and exothermic? So guys, when you have to go from solid to liquid to gas, or directly from solid to the gas, you guys hopefully understand that if you're trying to change solid into a liquid, you need to add heat to it. So if you want to melt something or boil something, you have to put it on flame, you have to put it on heat. So you basically have to supply heat, you have to put in heat. And as you see, we are putting in heat. So this process on the top, going from left to the right, is called endothermic. So when you're going from left to the right, be it melting, boiling, or sublimation, that's endothermic process. So the opposite, going from gas to liquid, liquid to solid, which is called condensation and freezing, or even deposition directly from gas to the liquid, this is the opposite. This is called exothermic, because you need to remove heat from the steam if you want to condense it back to a liquid. And if you want to freeze that liquid to a solid, you have to remove the heat from the liquid, and that process that's why called exothermic, because the heat is leaving the liquid to change it into a solid. Okay. All right. Now, when so this is one of the examples that you're going to see for endothermic and exothermic. Okay. Now, if I give you some more examples, as I was talking earlier, guys, about the coffee cup. So if there's a hot coffee cup, and you take the coffee cup and you put it on a table, okay, and you let coffee cup cool down. So this was hot coffee cup. You let it cool down on a coffee table. On a table. Then you notice that the coffee cup itself is going to lose the heat. so the heat is exiting. So for a coffee cup, this process for the coffee cup, since it's losing heat, is going to be called exothermic because it's losing heat, it's cooling down. On the other hand, the tabletop itself is gaining that heat from the hot coffee cup, so it's gaining heat. And if something is gaining heat, the heat is coming in. If the heat is coming in, that process is going to be endothermic. Okay. Now, let me give you guys one more example. If you take, for instance, hand sanitizer, we're using that so many times these days. So guys, you must have felt that the hand sanitizers, when you put them on your hand, they feel very cold. Why do they feel cold? It is because, you see, when you put the hand sanitizer, which is basically alcohol, when you put alcohol on your hand, it's liquid. And you see how it evaporates into a gas. You see, after you rub alcohol on your hand, you don't have to dry it with a paper towel. The alcohol itself just evaporates into the air. So you see, when you're doing evaporation of alcohol on your hand, that is basically evaporation, so boiling or evaporation process, when you're changing liquid into a gas. And you guys know, changing liquid to a gas is endothermic. So if you take rubbing alcohol and you put rubbing alcohol on your hand, then the alcohol will change from liquid to gas. It will just distinguish, it will disappear. It will go from liquid to the gas. So for alcohol, that process is endothermic. But if we think about the hand itself, you see how it feels cold is because it lost the heat. Lost the heat. Who did it lost the heat to? This heat was lost to the alcohol. Alcohol gained the heat from the hand. So a hand who lost the heat, for the hand, this is an exothermic process. So every time, guys, when you read a question, so if the question says that when you rub alcohol on your hand, then for the alcohol, that process is what? That process for the alcohol is endothermic. But if we change the question, that what is this process for the hand, and for the hand, that same process is exothermic. Okay, so you have to be very careful when you're answering the question, that what is the question's focus on? Is the focus on the alcohol, or is the focus on the hand? Is the focus on the coffee cup, or is the focus on the table? Okay, based on that, your answers will differ. Okay. All right, so guys, that was your endothermic, exothermic. Now we got to look at the graphs for endothermic and exothermic. And guys, you're going to be seeing this also as your extra credit question on your exam, on exam 3. So guys, what basically we'll do is you'll see, you have to draw, you basically have to draw a reaction. Take another page. Okay, so you have to try to draw a reaction where we label the x-axis as reaction, and we label this y-axis as energy. So what happens here, guys, if let's say let's go back to that example of sugar that we were taking, C6H12O6 plus oxygen, glucose in presence of oxygen. When you do the combustion, you make carbon dioxide and you make water, and this gives off energy. And if you guys remember, since it's giving out energy, this reaction is exothermic. Okay, so let's say if you have to draw that on this graph, we basically need to show whose energy is more, guys. See, C6H12 has more energy stored in it. That's why when it changes to CO2, it is able to give off the energy. Okay, and the opposite of this is also true. If we take CO2 and water and we change it into C6H12O6 plus oxygen, which basically is an endothermic reaction. Why is this endo? Because you have to supply energy. You have to put in energy in this reaction to form glucose and oxygen. And that's why this is an endothermic reaction. Okay, so if you have to draw that here, we basically need to draw that where is the reactant going to be and where is the product going to be. So that's what we're going to show here. If I'm drawing this label, if this is higher than this one, what is that trying to show? That this is higher, meaning it has more energy. You see, y-axis is energy. So something that is higher has more energy, and something that is low has low energy. If I look here, this one has low energy and this one has high energy. When the reaction is proceeding, guys, as you begin with, let's say you start at 0 seconds, no reaction has happened. Then after 1 minute, reaction is complete. All the reactants have changed to a product. So if I say here that the reactants, you start with reactant and you go to product. Here also you start with reactant and you go to product. Do you notice that in this reaction, reactant, you have to actually put in energy into the reaction? So you have to supply energy. So you're putting in energy to the reactant so that the reactant's energy go high and it becomes a product. Okay, since you are putting in energy, this is an endothermic example. So when I ask you to draw the graph for endothermic, this is what you're going to draw. So this reaction right here is an endothermic reaction. Okay, now in this case, when you're going from a reactant to the product, you see how there has to be a decline in the energy from reactant to the product. So reactant is high energy, product is low energy. Where did that energy go? That energy was lost or given off, or it exited. Since the energy is exiting, it's coming out, this going from reactant to the product when the energy is lost, this is the graph for exothermic reaction. So if I ask you in the exam to draw exothermic, this is what you're going to draw. Reactant on the top and product on the bottom. If I ask you to draw endothermic, then reactant in the bottom and product should be on the top. Okay, and please remember that reactant is always written first. You see it's in the bottom, but it's reactant first. You see even here, reactant is written first and then the product. Why is that, guys? Because if you see, when you start the reaction, so when the reaction starts, this is the start and this is the end. When the reaction starts, you have reactant. When the reaction ends, you have product. Same thing here. When the reaction starts, you have the reactant. When your reaction is done at the end, you have product. So always label reactant first and then the product. Reactant first and then the product. If the energy is coming in, that's endo. If the reaction is, if the energy is going out, that's exo. Okay. So hope, guys, that makes sense. What we're going to do now is we're going to continue with our next topic for this. Okay. So let me get a new page. All right, guys. So if you guys remember, I showed you the equation as we were doing earlier in the lecture. We learned that Q is equal to mc delta T. Okay. Okay. Let me take out some questions from the chapter 6 slide, so you guys can find these slides also on Canvas. So we talked about the energy itself. We talked about the unit conversion. I'm going to come back to this slide, but let's just first go to the question for Q equals mc delta T. Let me see if I can find that question. It's even here. It's not here. Okay. Let me show you guys from your worksheet. Okay. Chapter 6 worksheet. All right, so guys, let's look at this question, okay? So the question here says, how many calories of heat, so you remember a calorie is a unit for heat. So basically, how many calories of heat may mean that they're looking for Q, right? So heat symbol was Q. So how much energy would be needed to raise the temperature of 12.4 grams of water from 21 degrees Celsius to 55 degrees Celsius, and the specific heat of water is 1 calories per gram degree Celsius, okay? So let me Okay, so as we were saying, guys, we were looking for the calories of heat. So basically, we were looking for Q. So Q is what we were looking for, and then our equation looked like Q equals mc delta T. So let's first make a list of what is actually given. Okay. So how many calories of heat would be needed to raise the temperature of 12.4 grams? So grams, guys, that's the mass. So we're given mass. Mass is 12.4 grams of water. So we have 12.4 grams of H2O. And then we're given the temperature. So it says you want to increase the temperature of 12.4 grams of water from 21 to 55. So that means that we're given the initial temperature which is 21 degrees Celsius, and then we're given the final temperature, which is 55 degrees Celsius. Okay, and then what else are we given? The question says that the specific heat, remember specific heat, which is C or something also labeled as S. So C for this question, so C for H2O is given to us, which is 1 calorie per gram degree Celsius, okay? So if you look at this equation, guys, we're looking for Q, that's good. And then M, mass, do we have the mass? Yes, we have the mass, 12.4 grams of water. Do we have the value of C, which is the specific heat capacity? Yes, we're given that as well. Do we have the delta T? Now, guys, again, if you see what does delta T mean, delta T actually means TF minus T initial. So T final minus T initial. So if we first try to figure out the delta T, guys, TF, if you look at here, TF is 55 degrees Celsius. So 55 degrees Celsius minus initial temperature, which is 21 degrees Celsius. So guys, if we take a look here, 55 minus 21, that's 34 degrees Celsius. So guess our delta T is 34 degrees Celsius. So let's take all these numbers and put them in this equation. Q equals mc delta T. Our mass, the first thing that's given to us is 12.4 grams times the specific capacity, that's 1 calorie per gram degree Celsius. And then the delta T, and delta T we just figured out, it's 34 degrees Celsius. So I guess if you see to our units work here, do they cancel? So you see grams, grams cancel, Celsius, Celsius cancel, then we'll be left with calories, and that's what we wanted. So if we take our calculator and then we do 12, if you do, let me do that right here. So if you do 12.4 times 34, then the answer you get is 421.6 calories. That's the unit we're left with, and that's what we actually wanted, calories of heat. So guys, that's your answer. So you should expect a question like this on your quiz and your exam, okay? Now let's actually take another look at one or three more questions that you actually see here. Let's discuss this question, and this will actually make you understand what is the significance of specific heat capacity. So if you guys take a look at this question, guys, is talking about so the question says if the same amount of heat, so you supply the same amount of heat to 10 grams of each of the sample of aluminum, iron, and copper. So you have aluminum, iron, copper, and iron. So you have these three things. You have 10 grams of each sample, and you try to supply heat to each one of them. And how much heat, whatever amount of heat it is the same amount of heat. So there's actually no math in this question. This is a conceptual question. So the question says you have 10 grams of samples of each one of these, and they all are initially at 15 degrees Celsius. They say, which metal do you think is going to reach the highest temperature? So if you guys understand specific heat capacity, which is given to us here, if you look at these three numbers, 0.215 for aluminum, 0.092 for copper, 0.108 for iron, what does this mean? You see, copper has the smallest number. What does that mean? That means that you need the smallest amount of heat to increase the temperature of copper. So if you apply the same amount of heat to aluminum, copper, and iron, copper's temperature is going to shoot up because its specific heat capacity is too low. Okay, so you can see how we can look at this data and tell copper is the easiest to heat, so its temperature is going to go to the highest. So that's the answer for that part. That's the copper. Then the question says, can you use the specific heat capacity data to tell gold from lead? So can you differentiate gold and lead from their specific heat capacity? Actually, see, what is this question trying to say? If you go back to that example that we were seeing earlier, you see how if these three metals, if I gave you these three metals and I told you that we don't know what these metals are, then you would have simply taken these three samples and then you would have heated them. And whichever one would have heated the quickest, or the one which would be the hottest one at the end of your heating, you're going to say, okay, that's copper. So you see how you can distinguish different metals from each other based off their specific heat capacity. So they're saying, look at the data for lead and gold. Do you notice their numbers are the same? So basically, if you heat the same amount of lead and copper with the same amount of heat, their temperature change is actually going to be exact same because you have the same amount and they have the same specific heat capacity. So by just simply doing this experiment of heating them, you will not be able to distinguish lead from gold. Okay, so that's the answer for this part. That's not going to work. Okay, so guys, make sure you guys work on these questions that you see in this list here. So these are some math questions. Then for exo-endothermic, you should understand exo and endo. You should understand their graphs.
you should also see this delta H is positive or negative, guys. Let me go back to that uh, to that um, uh, to that graph that we drew in the beginning. I forgot to mention, guys. Remember, the reactant was sitting here and product was sitting here, and this was the energy. So this way, and the other one that we had a reactant higher, and the product was lower. And again, this is still energy. So if I ask you, find the change in energy, how will you find the change in energy? So change in energy, this is sometimes also called as change in enthalpy. We don't go into much detail on what's the difference between enthalpy and energy in introchem. So for right now, just understand that just assume that they're the same thing, okay? So if you're trying to figure out what is the change in energy, what you do is you take the energy of product and then you subtract the energy of the reactant. Okay. So let's just assume some numbers so that it can become more simple for us to understand this. Okay. So let's say the energy for reactant here is 10 calories. And if I go up here, let's say this number here is 50 calories. Okay. Now let's do the math. The energy of the product is how much? It's 50 calories minus what is the energy of the reactant? It's 10 calories. So what do you say? What is your delta E or delta H equal to? Your delta E or delta H is basically equal to 50 minus 10, which is 40 calories. And you see how this number is positive? There's a big number minus a small number. So your delta E comes out to be positive. And if you guys remember, this reaction right here, when you go from reactant to the product and your reactant is low energy, product is high energy, remember you have to supply energy in these cases. So you have to put in energy. So this was the example of endo. And if you remember this one, reacting to product, this was exo. The energy has to leave the system. That's when the reactant will become a low energy product. So it must have lost the energy. That's why you see reactant's energy dropped and it became a product. So if we do the same thing here, if we try to find the delta E, which is the energy of product, minus the energy of the reactant. If I simply give these guys the same number, so let's say the product this time is the one who is 10 calories, and let's say the reactant is the one who is 50 calories. So if you simply do the math here, the energy of the product is 10 calories minus the energy of the reactant, which is 50 calories, you see that the difference is negative 40 calories. So you see how the delta E uh, so delta energy for the exothermic reactions is going to be a negative number. Okay, so actually this is an indication. If your delta E is positive, or if delta E is negative, what does that indicate? Positive indicates it's an endothermic reaction, and negative number indicates it's an exothermic reaction. Okay, all right.